Good afternoon, everyone. So welcome to lecture 7. We'll quickly conclude our discussion on quasi-convexity and move on to subgradient and its calculus. And let's see how much we can talk about the necessary and sufficient conditions for optimization. So you might recall that we discussed the sublevel sets of convex functions. And that is our basic motivation for quasi-convexity. So the trajectory will be sublevel sets, and I had given you a homework problem, right? Question is convexity of sublevel sets. Is it equal to function convexity, right? This was a question, right? And what is your answer? We had already shown the implication in one direction, which is if a function is convex, all its sublevel sets are convex, right? That intuition is clear. This we proved and illustrated. Right? So this is basically an illustration, but right, we proved this. If function is convex, its alpha level sublevel set is a convex set for every value of alpha. It's really by first principles. We will not spend more time, right? The proof is all there. But then I left you with a question. What if the sublevel sets are all convex? Can you prove the other direction? Yes, any responses? Sorry? Not true. So need not be, right? Need not be. And what is the counterexample? Did you delve further into it? I give one example here. Is that indeed a function, or rather, are all these sublevel sets convex? Log of absolute value of x. Is that a convex function, by the way? Log of absolute value of x? It's not a convex function. You can verify that. But, okay, say log of absolute value of x. And if you consider all the sublevel sets, log is log monotonically increasing with positive arguments? It is, right? So if I say log of absolute value of x is less than or equal to alpha 1, right? What is that amounting to saying? That x must be between e raised to minus alpha 1 and e raised to alpha 1. right? Basically, this set is nothing but in fact the closed interval e raised to minus alpha 1. It is x, sorry, x such that blah blah blah. This. These sublevel sets are all convex. Any alpha 1 you take, you're looking at a closed interval. You're all convex. So you have convex sets, but the function is not convex. Right? So you have a counter example. Counter example to the claim that all sublevel set convex could imply that the function is convex. This is a claim to which you have found a counter example. So therefore, they're not equivalent. Functions with all sublevel sets being convex are not equivalent to convex functions. Is that clear? However, there's something very interesting going on here. See, if you take a function like this, alpha is basically saying I put some kind of clip, right? So shrinking the alpha corresponds to downward movement along the function axis for a convex function. Is shrinking, right? But what does this mean, right? To say that all sublevel sets are convex also, I mean, I can't just dismiss it off, right? It also looks like a very attractive condition to meet. I mean, it's also shrinking potentially. And no matter where I clip, I'll end up getting a convex set. So this is what gives us a new name, quasi-convexity, right? So yes, functions with sublevel sets, which are all convex, have a special name. They're called quasi-convex functions. Okay, quasi-convex. I'll just give it L alpha. I just call it L alpha. His name for the sublevel set. Now, do they have some interesting properties? Let's understand this a little bit more, right? Functions which have this property. All these L alphas are convex. Okay, so this is just, I just stated whatever is on the board. The converse of this theorem doesn't hold. This converse doesn't hold. Sublevel sets don't imply, convexity of sublevel sets doesn't imply function convexity. And we took a very simple example. I've taken another example. Fx is equal to x1, x2 divided by 1 plus 2 x1 square. Again, you can look at the zero sublevel set, which is convex. Function is not convex. You can take log absolute value of x. It is a convex for all values of alpha. Still, function is not convex. The sublevel sets are convex for all values of alpha. Okay, so this gives us the notion of quasi-convexity, which if it's all sublevel sets are convex sets. Now, is that interesting beyond just a weird function like, log of absolute value of x? Indeed, log of absolute value of x is not weird. It is prototypical as actually of a larger class of functions. What you see in the board here are your favorite Gaussian functions, right? The Gaussian functional form, in fact, if you look at the negative of the normal distribution, you can show that it is actually quasi-convex. Okay. In fact, I have shown this for function of a single dimensional x, right? Fx is minus exp minus of x minus mu square, a simple function. So f dash x is 2x minus mu, blah, blah, blah. You can find a double derivative. This was a homework problem, right? I hope you tried writing down the tried and showed potentially the convexity of f, and you find that it is not. You can try using the definition of convexity or just the second derivative test, which you would have probably done, right, in your calculus 101. And here you find that double derivative is less than 0 for x minus mu square greater than half. And that's what happens, right? If x minus mu square is greater than half, suddenly you start seeing a very different behavior. So while I give the example of log 1 upon x, a more classic example is, and this is a single dimensional variable. So this value x minus mu square greater than half, or greater than equal to greater than half, you'll find that suddenly the curvature has changed. From being convex, it has started becoming concave. So, what about quasi-convexity? Function is not convex everywhere, but quasi-convexity you can easily show that it is convex. Right? All these, what are these level curves? What do the discs look like? The level discs or whatever level, not sub-level sets. Sub-level sets is the right word. What do the sub-level sets look like? If you slice this Gaussian or negative Gaussian, what do the sub-level sets look like? Actually, you should do it for the negative Gaussian. For Gaussian, you should look at the super level sets, the interior of the sub-level sets, interior of the negative Gaussian are the sub-level sets. So what do they look like? For the Gaussian itself, you will have to look at the super level sets exterior. So what do they look like? Yes, just turn it upside down, slice it. You must have seen the favorite depiction of what are these? I should fill them up ideally. Yes, what are these? Ellipsoids. We have done ellipsoids, right? So you can show that each of them is an ellipsoid. Have you never seen the graphical depiction of, right, these level curves? Is at least what you have seen. You have not seen sub-level sets of negative Gaussian, but level curves are always right? Elliptical. So what do you do to prove that the function is quasi-convex? What will you do? Basically use the first principles, right? I've done this here. You can see all of these. These are super level sets. Actually, I should, these are Gaussians. I'll just rename it. It's super level sets for the Gaussian. Can in fact verify that the Hessian or whatever the double derivatives. We'll look at the Hessian test today, or hopefully soon. But the double derivative test will tell you that these slices are not the function plotted along individual directions is not convex. Okay, this clear? This is making a case for quasi-convexity. Quasi-convexity is actually quite common. Mhm. Okay, so yeah, this is the proof. To prove that the function is quasi-convex, what would you do? You would use the first principles. Actually, write down these, right? F of x1 less than or equal to c1. How will it a functional form look like? Right, and that should give you that should give you this form. And it has, in fact, infinitely many sublevel sets that are convex. This is how it look like. You slice. So I think you have an idea how to prove, right? Question is, okay, all this is interesting. You have sufficiently motivated quasi-convexity. What could be good algorithmic principles for optimizing quasi-convex functions? Right? We have not yet talked about algorithms, okay? Right? But if quasi-convexity has nice properties like convexity, it would be great. That actually expands our horizon. Right? You're not just looking at convex functions or convex regions of functions. You can look at quasi-convex regions of functions as well. So any thoughts? We're not going to discuss algorithms right now. But since we have bumped into quasi-convexity unknowingly, we'd like to know, well, what could you do? So convex functions, you could do a descent, right? We have shown in the last class, the negative of the gradient will point in decreasing values of the function with respect to your sublevel sets. We have shown that. Quasi-convexity also, do you think we can just use the same principle of descent of gradient? No? You feel no? Oh, you're saying the function may not be differentiable. Okay, interesting. Well, well, that's true with convex functions also. It may not be differentiable, right? Are all convex functions differentiable? No. So he feels descent will work. So looks like it will work. You'll have to take some additional care on the curvature of the function. So do you think the gradient adjusted with the curvature, maybe the Hessian, right? The sign will flip. So you're saying descent should still work. Exactly. So you will have to do some adjustment of the gradient with the curvature. The curvature is the double derivative. So when we do double derivatives, so I think good point. So what we have made a case for is it's not sufficient, right? A quasi-convexity so makes a case for looking beyond first order moments. What is the first order moment? Gradient. And investigate second order. Right. Second example of second order properties is the Hessian. But properties in terms of what on the Hessian, right? We'll come to that. So we are also basically saying that we need to look at curvature. makes a case for looking beyond first order property and investigate second order property and curvature. I mean, or local curvature. Or curvature in the vicinity. Okay. That will also bring us not just to second order properties, but in terms of lower bounding curvatures, let's say through strong convexity, but also upper bounding curvature through Lipschitz properties. Okay. So it's not only Hessian. I'll put all the keywords. Strong convexity, Lipschitz properties, called Lipschitz smoothness. Let's just call it Lipschitz properties because there are two properties we'll talk about. So just register these keywords for now. Good discussion. Right? Now coming back to your point, right? What about the gradient, existence of gradient itself? It's a very interesting point you brought up. So it turns out that if the function is convex, you may not have a gradient, but there's a guaranteed subgradient, which is like an equivalent of gradient, even if the function is not differentiable. And I'll talk about that today. And the other interesting property is that the subgradient is guaranteed only if it's convex. It's not guaranteed if it's not convex. So let's see that as we proceed. Okay, by the way, there's some papers starting in 2015. You should look at more recent papers. I've put some of them there. You can point to more papers which really talking about stochastic quasi-convex optimization and its variants. But none of those papers you'll find can escape talking, right? Some escape talking about curvature properties, second order properties. Without that, really, you can't operate. You can see for yourself using the example of the negative of the Gaussian. Okay, so the spider near optimal non-convex optimization via stochastic path integrated, blah, blah, blah. Stochastic variance reduction for non-convex optimization. Variance, moment you say variance, you're talking about second order moments. And so on. Adaptive methods, okay. But do have a look. There's a lot more that's coming up. And I think there's a big area to explore. So that's the reason I spent a little time on quasi-convexity. Its motivation. Okay, so this is just a formal proof that the negative normal function is quasi-convex. So far I gave motivation, but it's very simple, right? Basically, the function will look like this: x such that minus of exp of minus of x minus mu square is less than or equal to alpha, which is nothing but x such that the norm of exp of minus x minus mu square is greater than or equal to alpha minus alpha. Just adjust the signs. Now you use the fact that just like we use the log monotonicity of log, you can use the monotonic increasing property of exp for x less than mu. But then for x greater than mu, it's monotonically decreasing. But in either case, it's basically a contiguous closed interval around mu. So very similar to this. Where was it? Yeah, I mean, I talked about this earlier. Basically looking at a closed interval. Yeah, sorry, here. E raised to minus alpha, e raised to alpha. Similarly, now you're now expanding this bounded interval in multiple dimensions. So these are actually ellipsoids. You can try writing it down. I won't spend more time on this. Yeah. Sorry, x minus mu less.
X less than, it would be x less than mu plus or minus.
Oh, yes, yes. Yeah. There's a small, yeah, there's a additive factor which I missed out. Okay. So this is the connection. I mean, this is similar in some sense to log of absolute value of x less than equal to alpha. Okay. So far, so what have we done? We have completed our understanding of quasi-convexity and sublevel sets of convex functions. Now we want to move. We have motivated, first order properties and also second order properties. But there's one more interesting, strong motivation for the first order and second order properties viewed through their epigraphs. Okay. In fact, the epigraph is interesting because it will give us some equivalent definitions. So far, I've given you a new territory called quasi-convexity. But let's come back to familiar territory of convexity itself. Can we characterize it using other properties? So I think that the image I'm going to, I would like you to stick around in your head. No, this is better. Yeah, the image I would like you to stick around in your head is the image I had shown of a bowl with a hyperplane subtending it at the bottom. But before we get there, I also want to motivate how this is all connected to even deep learning, right? While I've said it that in the past, I'm again re-emphasizing that many of these properties become extremely relevant when the moment you start looking at properties of the loss function with respect to selected set of weights, right, in deep networks, including transformers, right? So, for example, if you have frozen parameters, right, with pre-final parameters frozen, we're often dealing with convex regions. So looking at convex regions of loss with respect to a selected subset of these parameters becomes useful because most of the time we're actually doing differentiation, we are doing descent with respect to a subset of the parameters only. So convexity is quite natural there. Just that in the overall analysis, we have to do a little bit more beyond just convexity to ensure convergence, right? Because there's some engineering required to ensure that what you're assuming about convex regions also holds overall, right? But other than that, the motivation of convexity is fairly generic. Yeah, the point is underlined here. All this is applied extensively in convex regions of non-convex functions, even in deep learning. Okay, so now coming to the concept of epigraph. So epigraph is nothing but the region above the graph of the function. So this is a graph of the function, and this region is the epigraph. So it's very natural. If the function is convex, you would expect the epigraph to be convex, and in fact, vice versa. If the epigraph is convex, you would expect the function to be convex. And that proving that is not at all difficult. Okay, this is one of the simplest equivalence relationships. So, for example, affine functions of vectors A transpose x plus b. If you look at its epigraph, it's looking at the half space A transpose x plus b less than equal to t. And convex set. So, formally, we could prove that. Oh, by the way, this is a picture I'm trying to draw on the board, and this will build upon this image, right? Looking at all the points above the graph of the function. And I would, as a homework, I would like you to try plotting and inspecting not just this, but also what follows in terms of first order properties of these convex functions. Okay, so you can prove that a function is convex if and only if its epigraph is convex. So it's if and only if relationship as against quasi-convexity. F is convex if and only if APF is convex. Okay. So it's a bidirectional relationship. Evident from this image here, but you can also prove it from first principles. And you can show that you can start seeing the difference between the epigraph and the sublevel sets when you start showing the inequalities. In the case of sublevel sets, you were operating in one dimension lower. Whereas in epigraph, you're not really doing any projection. So that's where you're not lossy, right? The projections bring you some degree of loss. So that's the intuition why we see a difference between these two views of convex sets. One which is a lossy view in terms of sublevel sets, and the other is a non-lossy view. Okay. But then formally, we can show that if D is a non-empty convex set and F goes from D to R, then the statement of convexity of function F and the set epigraph F can be stated as follows. F is convex if and only if epigraph F is convex. So proof, you can do it in two ways. I mean, you need to do in two directions. F convex implies epigraph F is convex. The proof is exactly like for sublevel sets. Nothing changes at all. In fact, only difference will be that if x1, x2, xn comma alpha. So the difference is now you have brought in a new point alpha, right? Because you're now considering convex combination of 2 points here, right? So this is x1, x2, blah, 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 alpha. And this is another point, x1 prime, x2 prime, blah, 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 alpha prime. Now you have to show that the line segment joining these two should be lying inside the set. So that's the only difference you added an alpha, alpha prime. And then you show that this convex combination will also lie by virtue of the fact that for each of those combinations, the function f will be less than equal to the will be less than equal to the corresponding alpha or alpha prime. Right, that's what I've shown here. F of theta x1 plus 1 minus theta x2 is less than equal to theta of x1 plus 1 minus theta of x2, which each of which is less than equal to alpha 1 and alpha 2 respectively. And therefore, this inequality. Very simple. Right. So this proves it one way. The other way, how do you prove? Do you see how the proof the other way is actually very trivial extension of the same? By virtue of the fact that you are not projecting. Do you see the proof for the converse holds? Not the converse, sorry. The reverse holds, which is epigraph f is convex, implies the function f is convex. So what will you do here? If epigraph f is convex, what do you know? This. Sorry? What do you know when you say epigraph f is convex? What would you know? What would you insist about? Now, what is the weighted average? So you see, it's so evident. You're basically saying that this line segment should be lying inside. This line segment should be lying inside, which means that the function evaluated at so what is alpha 1? Alpha 1 is, remember the definition of epigraph. Epigraph is convex. First, you look at the convexity property, then invoke the fact that it's epigraph, which means f of x1, x2, blah, blah, blah is less than equal to alpha 1. So you have that additional inequality, right? So you have the property that this f of x1 is less than equal to alpha 1, f of x2 is less than equal to alpha 2. Sorry, there's a little bit of overloading here. This is x1, x2, x3. This x2 is the second component of the vector x. Right here, I'm referring to this x1 and x2 as two different points. Okay, I mean, it becomes very messy showing all that on the board. So better to stick to the notation on the slide. These are two different points. So I know that this inequality holds for epigraph. F of x1 less than equal to alpha 1, f of x2 less than equal to alpha 2. And then I know that the line segment joining these 2 points will lie completely within the set. By virtue of that, what do I know? that this inequality will hold, which is for every point, every convex combination, f of theta x1 plus f1 minus theta x2 will be less than equal to this inequality. Put these two together, you get the convexity of the function, which is this inequality. Is that clear? So I just show it in the next slide. But the idea is, as I said, hidden there. Since epigraph f is convex, you'll have the fact that theta x1 plus 1 minus theta x2, comma, theta alpha 1 plus 1 minus theta alpha 2 will be lying in the epigraph of f. So which implies, now what does it imply? Basically, for this to be lying inside the epigraph will mean that f of theta x1 plus 1 minus theta x2, if applied to this, should be less than equal to theta f of x1 plus 1 minus theta f x2 for any point, for any scalar theta in 0 and 1. This basically means that the function is convex. So super straightforward. So I just spent some time to help you understand and appreciate that there's seamless connection between function convexity and epigraph convexity. Okay. They're kind of two sides of the same coin. This brings us to the next important step. How is the epigraph useful? The epigraph is actually useful in visualizing and also building upon first order properties. Now, if the epigraph is convex everywhere, and it's a convex set, what do you know about convex sets? Do they have a supporting hyperplane? Are convex sets guaranteed to have supporting hyperplane at every point? The first order property is all about the characterization of the supporting hyperplane of the convex set called the epigraph. So you take any point here, you should have a supporting hyperplane, right? So first order convexity conditions boil down to supporting hyperplane on epigraph of F. So this is on a convex F. So look at it. Epigraph, if it's not a convex set, then the function is not convex. Remember that. They're equivalent. So if the epigraph looks like, no, if it doesn't look like this, if the epigraph were this, right, then the function is not convex. For a non-convex epigraph, non-convex set, supporting hyperplane is not guaranteed at many points. In fact, could be at a finite number of points. So if the supporting hyperplane is not there, the first order convexity condition won't hold. And therefore, what you were saying, the gradient existence, which is in terms of first order property, becomes a challenge. Is that clear? So don't even look at the definition here. The definitions here are just Right. For some reason, the recording stopped. Okay, so what's the question from someone? Yeah. That's where subgradients come in. So just wait. So when I say gradients, I mean the class of subdifferentials, right? A broader class, not just in derivatives. So you're spot on. So uh, let me restate what I was saying. If the function f is convex, by virtue of the fact that its epigraph is going to be convex, and the fact that the convex epigraph will have a supporting hyperplane everywhere, the original function will also have the equivalent of a gradient at every point. The equivalent of gradient for a non-differentiable function is a subgradient. Is this clear now? So we are not committing to gradients in terms of um, a stack of all the partial derivatives. By our notion of gradients is something that supports through the hyperplane. Right? Okay, so let me just write this down first, and then we'll talk about more. So what are we seeing here? This is saying existence of supporting hyperplane at every point x in terms of the gradient at x. Okay, this is what we're talking about here. And what is the exact form here? So this is basically this is a supporting hyperplane. Fx plus gradient transpose fx, gradient at fx transpose with dot product with y minus x. And you know that is how the supporting hyperplane looks like. So let's also put it on the board here. So recall, right? The gradient we had interpreted in the context of sublevel sets. What was the gradient looking like for sublevel sets? Right? If I were to project this, what was the gradient looking like? A vector in the x space, the D, right? The domain, pointing in the direction of increasing values of the function, right? Now, think of this as a projection, right? This is basically gradient is going to be in Rn, not Rn plus 1. But what have we done here? We have said, well, the supporting hyperplane will be characterized by this vector, but this vector is just giving you the direction. But there's one more component I'm adding to that vector, which is in terms of fx. So you see, think of this as gradient with a 1. Okay, so what is this? Let's actually write down. So think of this as dot product here, the supporting hyperplane, as a 1 followed by the gradient at x, dot product with fx and y minus x. Do the point x. Supporting hyperplane is for at point x, but you have to now show that this supports at x, which means for any other y, f of y is going to be greater than or equal to f of x, blah, 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 whatever, right? In fact, yeah. In fact, let me This should be fine. This should be. What do you know is the general equation of hyperplane? Y greater than or equal to A transpose X plus B, right? Well, let's use some different names. Otherwise, Y is also sitting here, X is also sitting here. So our Y here is slightly different. It is not the Y you were right. We were writing for the hyperplane, right? So let's call this P as a variable greater than or equal to A transpose Q plus R. This is how equation of hyperplane looks like, right? So our point currently is fx comma x, right? That is the point Q. Think of Q as fx comma x. And P is what? P is fy comma y. Fx comma x and fy comma y. Right? So what will this A be? What is this vector A? It's not just a gradient. Sorry? It's a normal to the hyperplane. But the normal to the hyperplane has two components. So I have written here a 1 under a gradient. Actually, it has a -1. It's a -1. See, you have to adjust for the sign here, right? So you as a homework, try and write this down. In fact, we'll do that very soon in on the slides itself. Just if you have to you have to rewrite this a little bit, and you will show that well the normal to the hyperplane is nothing but -1 comma gradient at x. there's a negative sign here because of the minus x. Okay. Now it turns out, so this is an interesting equivalent definition for convexity. Likewise, you have an equivalent definition for strict convexity. Okay. So the definition for strict convexity is in terms of this inequality just becoming strict inequality. That's it. No other difference. In the case of strong convexity, you have a kind of gap between the hyperplane and the function. So you're basically saying supporting hyperplane, but supporting hyperplane with a guaranteed supporting gap. In fact, it's a separate, think of it as a separating hyperplane. It's basically saying that the f of y should be greater than or equal to what the supporting hyperplane offers, plus a quadratic gap, a gap that quadratically increases in the distance between a point y and the point x. So at the point x, it's still supporting. So it is actually supporting hyperplane, but it's saying that at all other points, it cannot touch. The gap at all other points is quadratically increasing as the distance of that point is from x, right? So in the case of strong convexity, what are we saying? At the point x, yes, it is supporting. But as I move away from x, the gap is going to be at least quadratically increasing. So it's going to ensure that there is some sufficient breathing space in the case of strong convexity. Is that clear? Okay, so these are the key observations here. And I'm going to just bring back this view, right? So I said I will be talking about the gradient a little bit more. So at this point x, the supporting hyperplane, what we are looking at is the gradient fx, which is in the space, the space of the x, right? With a -1. See, it's basically pointing downwards. The normal to the, in fact, let me show it here. So this part in red, along with the -1, it's a normal to this supporting hyperplane. You see the -1 because it's pointing downwards. But more about this again. We'll keep revisiting this observation. Yeah, and I have kind of left a question for you to think about. Does this non-convex set have a supporting hyperplane at X? Right. So when I say I mean, this doesn't look like completely convex, right? Or in fact, if you think of dropping a point here, then certainly it is not convex. So you'll find that it is not necessarily going to have a supporting hyperplane, and therefore its corresponding function, the function was an epigraph, would not have the notion of a gradient. Okay, so how do you prove? So by the way, this is if and only. All these are if and only if conditions, and that is all because epigraph was on if and only if condition. So all this is fine with geometric intuition. How do you prove? Okay, I'm going to go through the proofs little quickly. I'll only point out one non-triviality in the proof. Okay, the trivial parts we'll just run over. So of the two, sufficiency is a very trivial part. What does sufficiency say? That if the first order condition holds. Okay, let's write down the first order condition on the board just once. I think we are done with sublevels. Okay. If you want, you can write it differently as well. That's okay. That's fine. Yeah. So I have actually used x1, x2 here, but that's okay. So if you take two instantiations of this with y replaced in one place with x1 and another similar inequality with x2. Yeah, is that what I've done? Yeah, exactly what I've done. So this y is x1, x2, and then there's a point x. Okay, one case it's x1, other case it's x2. The point x are considered to be theta x1 plus 1 minus theta x2. So you know that this inequality holds. If you take y to be x1, it should hold with theta equals x equals theta x1 plus 1 minus theta x2. Right? So I have just created two inequalities based on a specific set of x1, x2 and corresponding x. Now, when I instantiate, what will happen? I can actually just add them. See, my intention is to get this cancelled out. What will y minus x look like in one case? So in one case, it will be, so this will become in one case x1 minus x. What is x1 minus x? X1 minus theta x1 minus 1 minus theta x2. You see the trick? It's just about choosing the right x1, x2, and theta as a function of x1. Sorry, x as a function of x1 and x2. So x1 minus x will become 1 minus theta x1 minus x2. Right? What is x2 minus x? Substitute x as theta x1 plus 1 minus theta x2. What is x2 minus x? What is it? theta x1 minus x2. This is the pure trick, right? Once I substitute, get these two inequalities, I add them up. These guys will get, I mean, my goal is to get them cancelled out. See, what is my goal? Goal is to get the original inequality for convexity, which didn't have gradients. I want to get rid of my gradients from the two inequalities. And that happens by virtue of this, right? One is 1 minus theta x1 minus x2, other is minus theta x1 minus x2. Actually, yeah, I think, did I write it correctly? Yeah, I think this should be fine. Okay, so so if you consider these two, adding 1 minus theta times, there's a small trick. You're not just adding those two inequalities, you're also saying, well, the first inequality will have theta x1 and multiply, right? So I want these two to cancel out, right? What will I do? With this, I'll multiply a theta. With this, I'll multiply a 1 minus theta. That's the other trick. Multiply inequality by, I think this should be multiplied by theta multiply inequality by 1 minus theta. That's it. Okay, you'll see the whole thing unfolding on the slide. On the board, I'm just giving you the intuition. Okay. So what are we doing? We have these two inequality, f of x1 plus f of x1 greater than f of x plus theta, gradient transpose fx x1 minus x. Fx x2 is greater than equal to f of x plus gradient transpose theta x2 minus x. I will take 1 minus theta times the first and theta times the second inequality and add them. And that is the effect I have explained on the board. Right? The effect will be what? You'll get theta f of x1 plus 1 minus theta of f of x2 is greater than equal to f of x. This part will get cancelled out across the two inequalities. Is that clear? There's no point repeating what is there on the slide on the board, right? So I'm just giving you the intuition on the board. Is this clear? So convexity, we have showed that the first order condition is sufficient for convexity. The existence of a hyperplane will mean basically, in terms of the gradient, means that the function is convex. Now what happens in the case of strict convexity? This inequality will be a strict inequality. So what follows will also be strict. Nothing changes, right? See, you guys have to look at the slides beforehand. I post them beforehand, right? So, so in the case of strict convexity, strict inequality holds. In the case of strong inequality, more work is required. Little bit more work is required, which I will not do in this. On the, I just want you to recap, right? What is the case of strong convexity? You have everything is correct, everything is the same, except that you have plus 1/2 c y minus x square, right? So I'll use a different color for this. Plus 1/2 c norm of y minus x square. So imagine I do all this substitution. I put x1 minus x, no, y as x1, y as x2, and x is equal to theta x1 plus 1 minus theta x2. I'll have some quadratic term sitting around. I have to do some algebra to simplify those quadratic expressions, right? So there is some manipulation, but the things work out very nicely. So what you'll get eventually is this theta f of x1 minus c by 2 norm x1 square plus 1 minus theta f of x2 minus c by 2 norm x2 square. And that you can show is greater than equal to f of x minus c by 2 norm x square. It's just, just by substituting for x as theta x1 plus 1 minus theta x2. So what was the original definition of strong convexity? Yes, what was the original definition of strong convexity? Yes, f of theta x1 plus 1 minus theta x2 is less than equal to f of theta times f of x1 plus 1 minus theta f of x2 plus what was that quadratic term? It's the same c by 2, right? Half c by 2. No, c by 2 that is into here it was just y minus x. What was it there? What was the quadratic term there? Theta. Was it theta 1? Theta times theta 1 minus theta. Is that correct? And did it involve a difference between x1 and x2? Okay. Okay, so you can verify that. This is substitution. You'll get the same term. Only differences now we'll talk about. Yeah, you should get this for x1 and x2. Correct. Okay, so with that, let's go to necessity. Necessity is also straightforward for most part. What is necessity saying? Well, if my second inequality holds, which is the original inequality, and forget this part, the strong convexity part will come later, right? If this inequality holds, then the first order inequality should hold. The only trick is I have to get a gradient somewhere. Somewhere gradient should start coming in. How does gradient come in? Okay, this is the only tricky part. Of course, there will be one more tricky part later on for strong convexity, for strict convexity, not for strong convexity. This is the only important step here. If f is convex, then we must have this inequality. What is our interpretation of this dot product of gradient and direction x2 minus x1? You remember last class? Yes, directional derivative. Right? So this is the scaled version. So this is not really directional derivative, because directional derivative requires you to divide by the norm of the direction. So x1 minus x2, I've considered its magnitude as well. So it's a scaled version of directional derivative at x1 along x2 minus x1. Right? So I've just shown this here. X2 minus f of x2 comma x1. So these are coordinates x1 and x2, whereas we are talking about 2 points x1 and x2, right? At two, so let's say x1 here and x2 here. So what is this hyperplane? This is a hyperplane, right? What is it representing? It is the magnitude of f of x plus theta y minus x minus f of x divided by theta. Okay, so this is another interesting manipulation. Let me show that on the board. Oh, I should not agree. Everyone, make sure you have this picture on your notebook. Always helps visualize. Okay, so the theta and 1 minus theta can be used very interestingly for our advantage. Okay, so we are going to look at f of x1. Okay, this is dot product itself. Differently. So yeah. So can I write this? So this dot product, how do I write it in terms of directional derivatives? What is the expression? The directional derivative was found to be a dot product of the gradient. That's how we discovered gradient. But go back to directional derivative. It is the, I mean, that we have written that, I've written that very loosely there, right? You take a direction theta, sorry, take a direction y minus x, right? This is limit as theta tends to 0 of f. Right? Now, I'm evaluating it at the point x1 along the direction x2 minus x1. So this direction is h. Let's just call it h. The only difference is this h is the direction x2 minus x1. Right? That's how we defined directional derivative. So I'm sorry, this minus f of x1. Okay, so now I want to rewrite this a little differently. So x1 plus theta x2 minus x1. Can I write that as a convex combination? Okay. Let's expand x1 minus theta x1. What is that? x1, 1 minus theta. And what is the second component? Plus theta x2 minus f of x1. The whole thing divided by h. You understand? I just reinterpreted my f of x1 plus theta h as f of a convex combination of x1 and x2 by virtue of the fact that h itself was a direction from x2 to x1. Sorry, from x1 to x2. Okay, so this is what we have done. Right, we have taken this right hand side f of x1 plus theta x2 minus x1 minus f of x1 divided by theta. Sorry, I have jumped one step ahead. Right, I have taken this to be the expression which I have showed on the board, which is f of the convex combination minus f of x1. And what do I know about this? I know that this is less than or equal to f of x2 minus f of x1. How? How do I know this? Yes? Sorry, somebody was saying something. By definition of which convexity? The first principles? The first line. This line. Yeah. So is this clear? See, this is necessity of that first order condition. We are saying that this necessity emerges from the fact that if you go back to the first principles definition of convexity f of theta x1 plus 1 minus theta f of x2, f of theta x1 plus 1 minus theta x2, which should be less than or equal to f of theta times f of x1 plus 1 minus theta f of x2. Then if you take now this limit property, right, just put the theta here. Take the theta on the right hand side. I mean, if this is not convincing, I'll just suggest doing the following. Okay, so this I'm saying okay, I just put a limit theta tends to 0. This part, okay, I'm sorry, this this is theta, the denominator. This part, f of x2 minus f of x1, multiply that by theta, right? If you just multiply this part with theta, you will get exactly the original convex inequality. So just multiply this with theta, you'll get the original convex inequality. Is it clear? Or if it's still not clear, I mean, I hope it's clear, right? If I just take this theta on the right hand side, right? F of theta x1 plus 1 minus theta x2 minus f of x1 is less than equal to f of, just subtract f of x1 from both left hand side and right hand side. This is less than equal to f of x2 minus f of x1 times what comes in the denominator? Did I subtract? No, I should actually, sorry, this should be subtracting x1. Wait. Was it theta? Oh, sorry. There's a theta x2 here. That is a different. Theta x2. This was theta x2. Theta x2. I'm sorry, there's a theta x2 here. We're dealing with theta x2 here. Right. So I just swapped it here. So theta x2 plus 1 minus theta x1. Yeah, everything is correct. Otherwise, minus f of x1. So this, all I've done is subtracted f of x1 from both left hand side and right hand side. And that should basically give you f of x2 minus f of x1 times theta. Or just theta of x2 minus f of x1. It's just manipulating the right hand side. So that's manipulating this by subtracting f of x1 from both sides. So just note that this is theta x2 plus 1 minus theta x1, not theta x1 plus 1 minus theta x2. That's how we assumed the left hand side to be, right? Okay. So now this is just basically giving us the first order property. Is this clear? Is this proof clear? This is just giving you the first order property that f of x2 is greater than or equal to f of x1 taken to the other side plus gradient at x1 transpose x2 minus x1. So this is actually straightforward for strong convexity as well. Strong convexity also you have to do something similar. Okay. The only tricky part that remains is strict convexity. What do you know about limits? What did we do? We took limit as theta tends to 0. We said the inequality holds by convexity. That's why we were able to show that this limit is less than or equal to f of x2 minus f of x1 with limit theta tending to 0, which was meaningless for a constant, right? But now imagine that we had a strict inequality here, okay? Strict inequality here. I take limits. With limits, will strict inequality be preserved? Do limits preserve strict inequality? Calculus 101. They don't, right? Limits don't preserve strict inequality. This you should recall. So that is where the problem is, right? And of all the hard work, original strict convexity definition at less than, I take limits theta going to 0 and suddenly now have the same definition as normal convexity. Where is a strict inequality in terms of strict supporting hyperplane? You understand this challenge? So the slides I present more hard work. How will you do? What is the extra hard work I'll have to do? Is this problem clear to everyone? Yes or no? Problem is with strict convexity, when I have a strict less than, right, strict inequality, and I take limits, limits won't preserve the strict inequality. So how do I show that despite the limits, I will still have strict inequality? What will I do? I've given a hint on the slide. What am I doing there? Suppose equality does hold in the case of strict convexity. Let's say for some point x2 and x1, there is a strict inequality. Right? How do you show that there must be a strict inequality by presenting a contradiction. So suppose there was an inequality for x1 equals x1 comma x2, right? Which is not the same. X2 should not be the same as x1. Then what would happen? It would result in the original inequality itself getting violated. Is that clear? The rest is again hard work, right? So yeah, I will not again go into the details here. You have to basically show that this will lead to violation. So here's a violation. If we had equality for x1 not equal to x2, then you will have violation of convexity itself. That's what we have shown. Okay. Violation of the first order definition of convexity, which we have already proved. Again, I'm not going to spend time doing this. You can read it up. And in the case of strong convexity, there is some little bit additional work you have to do, but it's again not such a challenging thing. It's basically addition of this quadratic term. The quadratic term is a very straightforward incorporation. Okay. Okay, so I think you have now a picture, right? The proof apart, and there's some subtlety with respect to strict convexity. Otherwise, it's very intuitive, straightforward. The intuition was provided up front. So while I have shown this picture is in the 2D space, you can visualize this in 3D space as well here. Okay. So now what next? What do you think our first order definitions can lead us to? What next? They gave us supporting hyperplane. What was another motivation for a supporting hyperplane? What is the function if itself is not differentiable? Okay. So next steps. Let's kind of speculate where we could go next. Okay, so the first step. Non-differentiable convex X. What else? So some things for non-differentiable convex X. What else? We should also be able to characterize second order curvature and all that, right? That's still right. Quasi-convexity. So basically curvature. The moment say quasi-convexity, we're looking at right? Curvature. That will lead to Hessian second order properties. And it also leads to other properties called Lipschitz properties. What else? We should start talking about conditions for optimality. All this is useful when I am able to optimize a function, right? Conditions for optimality of fx at x star. So basically x star as argmin over x and d of fx. What are the conditions? Can I use first order, second order properties, etc.? Subgrade, the non-differentiable natures of convex set, which is the subgrade, sub-differentials. And the fourth, which is algorithms. We want to move as fast as possible to algorithms, but we will iterate between algorithms and conditions, because conditions for optimality can be for non-trivial functions, for for functions with constraints, right? So points 3 and 4, which is conditions for optimality and algorithms, there will be a little bit of iterative treatment, but this is largely what we have remaining, right? And of course, convergence properties. When I say algorithms, we don't want to just do algorithms, but understand that algorithms and convergence. That's why strong convexity, curvature, all of that start mattering. Is this clear? The big picture? Okay. So we'll just do a little bit of second order conditions, the curvature part, which is the second part, right? So let's understand a little bit more on second order conditions, and we'll conclude with that today. So the second order conditions are in terms of the Hessian. One set of second order conditions. We look at more curvature conditions, but curvature in terms of second order is in terms of Hessian. Now it turns out that if the function is convex, then the Hessian must be positive, semi-definite. Okay. I mean, this notation is Hessian is kind of partial inequality greater than or equal to 0. So whatever I wrote here, right, this can also be written as the Hessian fx partial inequality greater than or equal to 0. So instead of saying this for all y, this was saying for all y, you should have this condition. Here you are saying, well, make sure that at every point x, the Hessian is positive, semi-definite. Is this clear? So this, again, again, I don't want to get into detailed proofs. These are equivalent. Sorry, I'll use a different color here, because this yellow is preserved for strong convexity. Okay. And moment you get in strong convexity, you will say the Hessian fx is greater than or equal to c times I. Some c, the same constant c. You're basically saying that Hessian minus ci is positive semi-definite. The curvature you're saying has at least so much curve with respect to the identity. Okay, so same kind of extrapolation, right? So what I've tried to do is giving you a homework problem. Can we use this condition to show that log sum x? You remember log sum x, our favorite function form, because it's very canonical for machine learning problems. Can you use this to show that log sum x is convex? Please try doing this, right? And the answer is, of course, yes. Boyd's book uses the fact that Hessian being positive semi-definite is necessary and sufficient condition for convexity. So this Stephen Boyd's book on convex optimization. Right. So what we will do, I mean, I'm inspiring you to do this as follows. You take a vector V transpose, the Hessian of the log sum x times the vector V. That's a quadratic expansion, right? What does it mean for Hessian, for matrix to be positive semi-definite? V matrix V transpose should be, sorry, V transpose matrix V should be greater than or equal to 0. Just try writing it. You'll start appreciating how these terms start interacting. Okay. And you can start seeing its relationship with the curvature. What is the curvature here basically saying? Well, originally we said the gradient gives you a supporting hyperplane, right? It's a perpendicular to the supporting hyperplane basically. Here we are saying that if you consider any V in the two-dimensional space, or in this case x1, x2 space, the space of the domain, this V transpose Hessian V is basically a quadratic around that point. And we are saying that this quadratic, the local quadratic function around that point, must have positive curvature for any direction V. So take any, and this should be for any V, right? Remember, a matrix is positive semi-definite if, okay, so just to remind you, what does this mean? This basically means that for all V, you should have V transpose Hessian V as greater than or equal to 0, right? For all directions V. So you take any direction V, the function, a quadratic around that function, based on, pivoted on V, should have positive curvature. Okay, so I leave you with this homework problem. Is clear? Please take these problems seriously, because that's when you will be able to deal with more non-trivial functions. We are giving canonical examples which will give you the capability to generalize the application. Thanks. We'll end up class here. So see you on Friday, and then next Monday I will not be available. I'll take the compensatory class on Tuesday. Thanks.